Welcome to the Todd and Noah Show, taking the mystery out of electric motors. Ooh.
Yeah, it's very scary. And hello.
Can be scary.
Sunny Tampa, Florida.
Hello, indeed. This is Noah Bethel, our Vice President of Product Development, and I am Todd Gunnarsson, the Vice President of Sales and Marketing for PDMA Corporation. And this is part of our 12-part series on taking the mystery out of electric motors.
Yes, indeed.
And the last one we talked about, we were going to share with them some information on how the power circuit can help save on efficiency.
That's right, the cliffhanger.
The cliffhanger. And what I'm going to read to you is a multi-year study from EPRI.
EPRI is a well-known organization, the Electric Power Research Institute.
Exactly.
Non-utility members out there.
And what they found was research on industrial power distribution systems has shown that connectors and conductors are the source of 46% of the faults, reducing motor efficiency.
Can we just round that up to 50? Like just half the problems
for you
are the root cause.
50% is doable.
50%. I mean, you're talking half the problems reduce your motor efficiency come from your power circuit.
Yeah.
Now, you got to care about efficiency, obviously, first, but most people should, and I guarantee that people are paying the bill.
I think more and more people are caring about it because energy costs are so high, you want to be efficient.
Well, the single largest lifetime cost of an electric motor is the power.
Power supplied to it, right?
Hands down.
Yeah, right. So efficiency should matter. If it doesn't, it should matter.
It should.
And there's ways that you can help reduce those anomalies that reduce the efficiency.
Absolutely.
Okay. So Noah, let's talk about the power circuit, because this is the podcast power circuit that we're on right now, and we're at power circuit.
And you know what? Here's what I like about power circuit is, and it does, I mean, back up a little bit, it does matter which situation your plant's in, right? Yeah. So like if you're a brand new plant, guess what we see? A lot of power circuit issues. If you're a very old plant, guess what we see? A lot of power circuit anomalies.
Right.
Right. And so a lot of times you got people going out and replacing this, replacing that, and they're ignoring that power circuit element. You know, can I tell you a case? Can I tell you a sea story?
A sea story?
Well, I know it's a strange name.
Sounds like a salty dog.
I know, but not really.
But you just heard that term 2 days ago. You never knew what a salty dog was. I had to tell you.
It must be
because
a surface.
It's got to be a surface thing.
So I'm in an aluminum plant, right? And so we're at the aluminum plant, and we're there to troubleshoot and this is like a 3,500 horsepower DC motor. Now, if you're not familiar with DC motors, a 3,500 horsepower DC motor, this was a top press, so they're pressing a giant piece of steel or aluminum into a skinny piece of aluminum. 3,500 horsepower DC motor has about a 6-foot diameter commutator. It's massive, right? It's a huge DC motor. It takes a special truck to move that DC motor from the facility to the local repair shop. You got to pull permits and the whole bit. It's a very big deal. Well, this armature had a large burnt, hole in the side of it. It had obviously blown. It was the second time it had blown in just the period of 1 year, right? So imagine the cost. We're talking approaching millions of dollars in repair and transportation costs and permits and all that kind of stuff. And you know what the problem was? In the power circuit. It wasn't the motor. It wasn't the power quality. The cable feeding the motor was underground and completely submerged. So they were literally starting this motor brand new at 0 meg.
Yeah, and you wouldn't think so being brand new, right?
You wouldn't think so. No, because guess what they tested? They tested the motor by itself.
Yeah.
All good.
Always.
No problem. Put it in, connect it, dead grounded. Now, as many don't know, but DC motors are the armature's a floating system. So brand new, it will run for 6 months, 8 months, depending on when the next ground starts.
Hits, and then boom, it doesn't run anymore.
Great sea story. 100% true. I was there to prove it.
So you kind of bring up a good case study or a sea story in respect to, how should you test? This question came up. We've got a junior employee that just came on board, and we're trying to share with him what are the right ways to test a motor. Let's say you got a brand new motor. You should test it before you accept it, right?
Absolutely. We mentioned quality control in a previous podcast.
Then maybe install it, test it again.
Absolutely.
Let's verify everything got tightened and everything is correct.
Right. Quality assurance doesn't stop at the truck.
Yeah, it doesn't stop there.
You want to make sure you didn't drive through the ditch on the way to your plant. Verify you got a good motor, but verify the system that you're connecting to the motor, i.e. the power circuit.
Yeah.
Verify that you're not putting this motor in jeopardy.
And now that's your baseline. That's where you start trending off of, because you have a known situation. You tested the motor, good. You tested the motor in the power circuit, good. Now you start.
Absolutely.
And test after that. So Noah, tell us, what are the components that make up the power circuit?
Well, there's a long list. Let's talk about some of the highlights, those things that we've seen produce problems in the power circuit, over the many years. A big one is disconnects, right? A lot of times, it doesn't, you have a starter, obviously, and that's a big deal. So you can look at the contactors, that's part of the power circuit. You could look at the fuses on the line side of the contactor being part of the power circuit, right? There's, another C story. I was on an offshore oil platform, and all the fuses were too short for the switchgear. So the right answer is to get new fuses. The wrong answer is
the quick answer is to just extend the length of the fuse.
Extended the fuse with this little jacket, and boom. And guess what? They had a lot of problems in the power circuit.
I would imagine high resistance connections galore.
It was a great day for the reliability team, for sure.
Yeah.
So that starter is a great place to start. Fuses, contactors, overloads are a big deal. When you go downstream from there, you've got a lot of times disconnects in between the starter and the motor.
Sure.
You've got the motor connection box, called many different things, but the connection box at the motor, these are lugs, these are taped. A lot of times they're not easy to see, but that's a very common place where things go bad. So anything loose or oxidized, terminal connections are something that does deteriorate over time. There can be defective cables. Cables can be the wrong size. What is the MCM level of one cable versus the other? Well, you hope you're replacing the same one. You get one bad cable on a 3-phase system. Let's make sure we're duplicating the size of the cable, because the larger the cable, the lower the resistance. This is changing the power circuit environment.
Right.
And of course, there's, I wouldn't dismiss, even like various components throughout the power factor correction capacitors and things like that.
Okay. So tell me, Noah, what, when I first came here, we used to say, when I was being taught on how to talk about the technology, talk about all the testing, if you see some loose connections out there, go out and have a screwdriver party.
Yeah, I think.
What are we really trying to do?
Are you talking about the drink?
Yes, that's exactly right. We would have vodka and orange juice, and that's what we had. That's the kind of screwdriver party that I thought initially, but I was just a junior nobody. But then they said, no, you got this. You got to go tighten things.
So if you were on a submarine fleet, you would have known that screwdriver party.
On a carrier fleet, screwdriver parties actually. Yeah, right.
Yeah, you guys did
it's the drink, the mimosa of.
Yeah, we weren't allowed to. In fact, any alcohol underneath.
We were not. Don't get me wrong. We were not allowed to have alcohol on the carrier either. It's just a common joke between Submariner and Surface that our lives were so much easier. Their lives were so terrible. It was so
uphill
difficult.
Both ways.
It snowed every day. It rained every day. That's all you hear from Submariners, and then Surface guys are like, "What are you talking about? Port and starboard duty? What?"
Those were
exactly.
But the screwdriver party is still important. I want to defend that because, again, one of the things that you can do with all this new technology that we have available, and it's great, don't get me wrong, everybody should be using it. But, it's looking for high resistance connections in the conductive power circuit, right? Even all the way down into the stator connections, right? Is it Y or delta connected? Those are connections that can go bad and be a power circuit anomaly. But what people sometimes forget with all this technology, measurements, you can look and verify that the power circuit's good. Well, what if the hardware supporting that power circuit falls off the back of the enclosure? So, the whole screwdriver party is extended not just to the direct line of connectivity, but to the support infrastructure around that.
Right. So talking about the power circuit, all that you just discussed, all the components in it, what type of tests should be done on it? What type of data should be collected?
Right. So one of the things we like to bring up in power circuit is the early indicators versus the later indicators. And different technology will indicate at a different time. You've heard us reference in the past the PF curve, right? The point of failure. And ideally, if you're following the general guideline for reliability, you want to find problems as early in that PF curve as possible, because as it falls off rapidly, and the later you catch it, the more expensive it's going to be, right, when you catch it. So infrared thermography and precision resistance are what we consider the most early indicators of power circuit anomalies. And this is a big deal because, like I said, when you talk about precision resistance, and again, we mentioned the larger the motor, the more critical that gets. they're going to see resistance.
You say
changes.
precision. What does that mean? What is precision? Is this down to the micron level that we're detecting insulation?
You hit it right in the
resistance?
nose. You know, you do need measurements on some of these larger motors to truly see the imbalances down into the million microamp level. Right? So yes,
okay.
by precision and the ability to repeat that test from point to point, temperature corrections on that to verify that you're not just seeing temperature changes.
Yeah.
You know, interesting enough, copper.
So you mean temperature changes by, like, say you go there today, and today is a very humid day, and let's say it's about 85 degrees Fahrenheit in Florida. But if we were to do this same motor that it's up in, say, Michigan right now, which is sleet or 15 degrees or 10 degrees, you may see some difference in...
Right, in a de-energized state, when that copper cools down to that 15 degrees, copper is a positive temperature coefficient. So if the temperature goes down, the resistance goes down. If the temperature goes up, the resistance goes up.
Okay.
That's not consistent for all of our fault zones, but for the power circuit and the copper specific environment, that's the case. So yes, you have to be aware of the temperatures and know that if that changes, that you need to be aware of that. One of the protecting elements is we don't just look at one phase. We look at three phases, and therefore, even if the temperature changes, you're going to be protected because we're focusing on the resistive imbalance, and that's what you want to make sure. Even if they all three cool down, the resistive imbalance may still be 1%.
So it's irrelevant.
Exactly.
It's irrelevant on that. So what else? What other data?
So I mentioned infrared pictures worth 1,000 words, right? That's going to be a big deal. You know, the two of them are going to be very early indicators, and let's bring that up just one more time, because if you see a high resistance connection using precision resistance, or you see a hot spot using thermography, the motor may not be affected by it immediately, right?
Yeah.
It's going to be a lot later in the fault mechanism before the motor starts to be affected. And this comes up when, like, say you're out there and you're doing precision resistance and you say, hey, this motor has a 3% resistive imbalance. It's gone up, it's doubled, it went up 300%.
So what you're saying is you may not see it in the current yet.
Exactly. And so your electrician may walk up, slap on his clamp-on ammeters, and he may say, hey, there's no current imbalance, because a lot of people feel like a high resistance connection is going to result in a current change, and it doesn't necessarily. Okay, there's a lot of localized heating that will occur. You can see it with thermography. You'll measure the resistance value, but it's going to be later before it affects the motor. Now, this should be a good thing. Catch it early, take care of it, so it doesn't ever affect the motor.
So when I'm doing workshops, that point that you just made, I tried to convey it through, let's say that you have you're talking about a big lake or an ocean, and you throw a rock, right? That rock at the point of impact is very turbulent, right? That's where all of the energy, but if you look at the whole volume of the ocean, nothing's happening there.
Right, it dissipates rapidly.
It dissipates rapidly, you don't see it. So is this the same kind of analogy that you would use with or could we use that analogy when we're discussing resistance, high resistance at a specific point that hasn't affected?
Absolutely, and there's no better comparison than to look at a thermography picture. If you look at a thermography picture of a high resistance connection, all that heat is right there, but you go 3 feet, 4 feet down the cable,
may not be there.
All of a sudden everything gets balanced again. So a lot of people, don't dismiss that though. They always say, hey, get it.
You need to know, right? Because at some point it could.
Right. Now, other than precision resistance, let's say, what can we do with the motor running? Well, now we start looking at current and voltage measurements, right?
Yeah.
And current and voltage is an important thing to discuss as well, because if you're seeing a change in current as a result of a power circuit anomaly, now we're later in the game, right?
Okay.
Still early enough to fix the problem, but you want to get it taken care of much more rapidly.
Right.
And so that's a big deal. The other thing to remember is voltage looks upstream. Right, so if you picture yourself at the switchgear, you open up the door, it's running, so you're of course completely protected, as you should be according to the site safety recommendations and guidelines. But if you clamp on voltage connections to that, and you clamp on current ammeters to do this test, right? Voltage, i.e. voltage imbalance, is looking upstream to the transformer. If there's a problem with a power circuit down at the connection of the motor, voltage will not see it. Because
we haven't had the voltage drop yet.
Exactly.
Is that what you're saying?
It's very location specific. Guess what's not location specific?
Current.
Current is a universal indicator. When you put current on, the power issue could be upstream or it could be downstream.
Yeah.
but yet you will see it with current.
Kind of like a burglar, something's
That's a
going
good
on.
example. We were talking about kids earlier, right?
Yeah.
Our burglar system is, our alarm system is great. It goes off.
Our kids are out of the house running amok.
Are they sneaking out of the house? Are they sneaking into the house? What are they doing?
Yeah.
Yeah. So
what are they doing?
Voltage is another very critical element when it comes to power circuit testing.
So Noah, you've described the power circuit really well and the components and how to test it. So now we're going to put you kind of to the test again. Another test here, right? We get calls all the time at PDMA Corporation because we provided technical support for the life of the equipment. So we're always going to get phone calls in now. This gentleman actually got a phone call on Sunday of all days, right?
It's always when things fail, right?
Why can't it be
maybe
Monday?
Friday night. Friday night they
Could be
fail.
worse. Friday, Saturday, are 3 days that
Those
you
are
just
popular failure days.
you don't want to get a failure call that day.
Worst case, Super Bowl Sunday.
Yeah, and this is what he had said. When you give a start command to a motor, run a few seconds, and then nothing. Now I'm going to share with you. It was in a high noise environment.
Okay.
Okay.
I'm thinking drives and
It could be.
Non-linear loads.
It was high. Just the plant environment itself was noisy.
Okay.
They did an inrush startup test for it, and when they ran this test, for the first 2 seconds, all you saw was go up, down to zero. So it would go up, just up and down, up and down, up and down, and then at 2 seconds, then it just stopped because it either overloads or what have you. It wouldn't go further. Maybe it was a
Right.
timeout or something.
So can I tell you this?
Yeah.
For a second. The inrush startup test, as you're describing. Okay, this is capturing current voltage. At the start of a motor.
At the start, and that's important, right?
Can I tell you, it is my favorite test of all tests. And again, there's all kinds of electrical tests you can run.
Yes.
But that inrush startup test is so telling. It's the most stressful time of a cross the line motor start. That's an important little element. But if you can actually watch what that motor goes through during this very stressful moment of its life, it tells a lot about the motor, right?
Yeah.
And so as you describe that either an RMS envelope of current or the raw data of current that you can see, if it's normally you see like a 5 to 10 times inrush on the current, and it's called the initial excitation current, if you want to call it.
Okay.
It's based totally on Ohm's law, effectively. But you get that inrush, and then it drops to a startup value, which is
that would be a normal startup.
Normal startup. What you're describing is almost like
it's trying to start,
up, drip, up,
can't
drip,
start.
up, drip, up, drip, up, and that starts to me to be leaning onto like a chattering contactor or something, where something is having difficulty actual closing. Now you can see it on a lot of the startups. We expect a single chatter, like when those contactors slam. They have a lot of springs and stuff to try to prevent it. Sliding of the contactors versus bang. But we expect a little, but not like you're describing.
Yeah, and you always mention this, I know, in your presentations and your workshops about use your senses.
Yes, onboard senses.
Touch, use our onboard. You already have onboard senses.
Nose.
Use your nose. Does something smell?
Yes.
Something's burning up. Noise. Use your ears.
Absolutely.
Taste. No, we don't recommend you tasting anything out in the plant, unless you're in a chocolate factory, of course. Then you can taste the product, right? I'd be a volunteer tester for that as well.
I always say let the new guy test them.
Not in a chocolate factory.
Not in a chocolate factory.
But you have your senses. You have your sight. You have your ears. Your hearing. You have your smell. But like I said, this was a very noisy, so we couldn't hear it, but we could visually see this on the inrush startup.
Oh, okay.
So you can visually see the motor trying to stop. So with our engineers back, we told them, because I think initially he came in thinking this was a rotor bar issue.
Oh wow.
That it was the rotor that was preventing this motor from starting. But after we saw the inrush, we said, nah, like you had said, and you picked up on this quickly, contact chatter. Look at the contactor. It may not be closing
right.
like it's supposed
you mentioned that inrush being such a comprehensive test. It looks at rotor, it looks at stator, it looks at the power system, it even looks at machine train, but it really works best if you have an existing test before that. And if you sit there and think, well, why is this motor tripping? Well, every motor has a trip set point, And you're supposed to be through that startup current and down to a normal full load in a certain period of time. If the contactor is in and out like it sounds like, then what you're going to do is you're going to reach that set point before the motor ever passes a startup, and it's going to trip.
Now, keep in mind, we're always going to tell them, listen, do a standard test. Look at resistance ground, capacitance ground, phase-to-phase resistance, phase-to-phase inductance to verify that your power circuit is good, clean, healthy working condition. We're going to tell them, look at your polarization index, verify that it's at a correct value and that the insulation is at good IEEE 43 values. And then once we've determined that everything else was good, we pointed back at the inrush startup spectrum there, and we said, look at that contactor. And lo and behold, they were able to go closer to it, listen to it with the ear right next to it, and they could hear chattering. And so then they were able to pull it and find out that the holding resistor was failing.
Right, and this makes a lot of sense. The holding resistor, primarily being used to reduce the amount of current flow to the closing contactor. And if that starts to fail, well, guess what? You're going to have a real hard time keeping that contactor closed. And it was probably intermittently opening with a high resistance connection, dropping the contactor in and out. And it makes sense, makes total sense what they saw. Thank goodness there was actually a current indication that, because ideally in a quieter environment, you'd hear this. It wouldn't be you could hear this and you start to question what's going on. But in a noisy environment, it makes sense they would overlook that.
So you solved the great job on that. We couldn't stump you again. One time, I'm going to get you on one of these. Maybe I'll off the wall ask you something there and you'll trip up. But I doubt it.
Don't bet against me.
I'm not going to bet against you. I don't have enough money to bet against you. So now I'm going to take you over into Saudi Arabia, where we were at a facility there.
I thought we said heat kills a motor.
It does, and let me tell you, it's a hot place to definitely in the summer period, and it's dry, and it's almost like, remember when we were in Vegas, 115 degrees?
Oh my gosh! Keep the children and the dog and the animals off the street.
115. We couldn't land on the tarmac of the plane because the wheels were going to melt to the tarmac, or we couldn't take off.
Why were we in Vegas? In that
we were at the ESA show that we were at. We went to ESA.
I figured it was work related. Nobody
it's always work related.
Go there at that kind of extreme.
Well, that's work related. Of course, it was work related. But we do get a nice steak dinner when we go there. We try to make sure that 115 degree heat. We better get a nice steak dinner. Okay. So we're in Saudi. We have an interesting situation where we see a 4160 volt motor that has a 2% resistive imbalance. Are we concerned about that?
We're big concerned, right? Normally, and we always talk about alarm set points at the motor versus alarm set points at the switchgear, right? When you're going through 1,000 feet of cable and all the connections that exist in the power circuit, you'll accept a higher resistive imbalance. But when you're motor only, you expect under 1% resistive imbalance. And when you're talking about medium voltage motors with form wound coils like you're talking about here, we're usually expecting to see like 0.0%
we do not
imbalance.
Our tolerances become very tight the larger the voltage of motor is.
Absolutely.
So what would you expect to see? What are the things that you would walk through on this if you saw a 2% resistive imbalance at the MCC? You're going to go back down, I'm sure you're going to go to the motor connection box there and start to maybe do a little pull test here and there with the motor secured?
Well, that's a good point you make, because like a lot of times, we mentioned that the connections, the loose connections occurring. If you're actually in a de-energized situation and you're concerned about power circuit issues, a lot of times you can look at the lug areas, especially if it's not a completely taped up portion of the system. It doesn't require that additional isolation or anything. A lot of times just pulling on one of the cables will actually pull right out of the lug, and that's a worst case scenario, but it has happened. What we like to always, synonymous almost with the power circuit troubleshooting, is divide and conquer.
Yeah.
That's the idea. You separate systems and see where the source comes from. Where is the root cause of the power circuit anomaly?
So they went to the motor connection box and they opened it up and they saw signs of heat on one of the phases. Now, can an improperly or a different size lug make a difference in this case?
Absolutely. You think about when you're applying a lug to the outer portion of the conduit, or the actual cable itself. You want 100% connectivity all the way around, 360 degrees. Assuming you're using the right, lug wrench or the lug tool, the compression, and it's squeezing that lug around the cable properly.
So if you used a larger lug on there, you could have trouble, is what you're saying.
You'll have gaps where it's not connecting. And absolutely, there's no question, and even worse, as you heat and cool the cables through normal operation, shutdowns and running, you're going to expand and contract that cable within the lug and further increase the resistances and create a high resistance connection.
So in this case here, Noah, they had 250 MCM versus a 350 MCM lug. Or they had put a 350 MCM lug on, and it was called for a 250 MCM lug. So like what you were saying, it was larger.
Yeah, and when you first put it on, it grabs.
It grabs.
It feels good. So the electrician or the technician is.
But if there's some looseness in there,
and it will get worse with time, which it obviously did. And in a big, medium voltage motor like that, it doesn't take much to start affecting the, the voltage going into the motor.
Yeah. So Noah, thank you. That was that's what it ended up being in a small lug. It can be that simple. Just a bad lug.
And if it gets bad enough, it'll be a single phase. And
You
now
could
you're
destroy a large 4160 volt motor, and those are expensive.
They are expensive.
For a simple fix. And
Right.
this was a simple fix. So that kind of, you solved 2 case studies for us. We appreciate it. As always, we thank you for your technical expertise that you're bringing to this podcast.
Thank you for the opportunity to share.
Okay, and we hope that you were able to get some value out of this podcast as well. The listeners in our audience, we really appreciate you tuning into us and listening to what we have to say. Now, next week, or the next podcast next month, when it's going to post, it's the Charlie Brown of fault zones, isn't it?
It really is. Everybody picks on insulation.
I know. It's there in the bathroom. Who fee fee fi fi fo fo fum? Who smells smoke in the auditorium?
That's right. When smoke.
Charlie Brown.
It's the last point of failure, but it's rarely the root cause.
Yeah.
But but this is important, and we're going to give all kinds of insights on how to make sure that when insulation does fail, is making sure that you get to the root cause.
Right. So you don't want to miss the Charlie Brown of fault zones, which is insulation. And we hope to see you when we present that. And as always, we appreciate your time. We hope that you are come back and see us on our next podcast. And until then, stay safe, have a great day, and we'll talk to you real soon. Once again, this is Noah Bethel, VP of Product Development. I'm Todd Gunderson, VP of Sales and Marketing for PDMA Corporation, and we're very happy and honored and humbled that you're able to speak, that you're able to listen to us. Thank you so much.
Thank you for joining us for this episode of the Todd and Noah Show. We'll be back for another episode very soon. In between, we hope to see you in the Mobius Connect online community where you can network, learn, and share with Todd and Noah and other industry professionals at mobiusconnect.com, and we will see you there soon.